It's a very good afternoon, everyone. So, I will in this class today we will just discuss about what is transformer and what is what you have studied. What are the concepts which you already studied in the previous classes? Just we will recall once again, and then to the actual subject that we will enter. Hope you all already watched the first video which I have shared in the group itself. Actually, yesterday, because of some login issue, I have not taken the live class. Offline, I have recorded the class and I have shared in the group. Hope you all have go through that. Okay. So in that class, I have explained you about the what are the syllabus content. That is what topics that we have, what are each and every module what you have that I have already shared in the last class. Okay. In the today's class, just before going to start the module 1, I just wanted to retrieve some concepts that you already studied in the basic electrical engineering. Okay, so in the basic electrical engineering already you studied about the transformers, single phase transformers. So what is a transformer? Transformer is nothing but the device which is helpful for to transfer the power from one circuit to another circuit. It is a static device which is helpful in transferring the power from one circuit to another circuit without changing in the frequency. For that purpose, we are using the transformer. So, using the transformer, either stepping up of level of voltage or stepping down the level of voltage, both will be the possible. For that purpose, we use the transformer. So during transferring the power from one circuit to another circuit, we can change the level of voltage from one circuit to another circuit. See, this is the schematic diagram which explains the transformer. Okay. So from one circuit to another circuit, while you are transferring the power, we can change the level of voltage. So if you are increasing the level of voltage with respect to this primary circuit, in the secondary circuit, if you are increasing the level of voltage, then it is called as a step up transformer. Okay. And with respect to primary winding, if you are decreasing the level of voltage onto the secondary winding, then it is a transformer what we are calling it as step down transformer. Okay. So basically there are two types of transformers. We have step up transformer and as well as step down transformer. Okay. In the case of step up transformer, with respect to primary, secondary level of voltage will be higher in value. In the case of step down transformer, with respect to primary winding, the secondary winding voltage will be the lesser in value. So based on this whether you are stepping up the level of voltage or stepping down the level of voltage, based on that we have the classification of the two transformers. So if you are increasing the level of voltage, we are calling it as step up transformer, and if you are decreasing the level of voltage with respect to primary, then it is called as step down transformer. Okay, so this is a schematic diagram which explains you the basic construction of the transformer. So the transformer mainly consisting of two parts. Okay, one is transformer core. This rectangle box is there, no, in this diagram. This is called as the transformer core. Usually the transformer core is designed with the magnetic material. So in the practical transformers, we are using CRGO silicon steel material. We are using CRGO silicon steel material we are using to manufacture the transformer core. Okay, and one more important part in the transformer is winding. This is transformer core, and these black lines which is there on the rectangle, right? So this one represents the winding. Usually the winding which is designed with the material called as copper. What material we are using to design the winding? It is copper material. Using the copper material, we will design the windings. Okay. Again, windings, two windings we will have in the transformer: primary winding and as well as a secondary winding. Already these are all the concepts which you already know, but just for the recall purpose, I am explaining you all this. Okay. Because very long back you have studied all those things, so I will just recall once again, and then we will enter into the actual subject, module number 1. So always for the primary winding we will give the supply voltage. Always to the secondary winding we will connect the load. Okay. So this is just a brief details about the transformer. Okay. Next, coming to the construction, already we know that is the transformer mainly consisting of the four important parts: windings, core, and the remaining two parts are transformer tank and as well as the bushings. Okay. Next, there are two important types of transformers we have. Based on the construction of the transformer, we have two types of the transformers we have. One is core type of transformer and the other one is shell type of transformer. Based on construction, we can classify the transformers into the two category. One is core type of transformer and the other one is shell type of transformer. See here the schematic diagram of both core type and as well as shell type of transformers which have been shown. Here it is shown that the core type of transformer it is. In this diagram there is a figure B, right? So it is a transformer which represents the core type of transformer. What is core type of transformer? How the construction of core type of transformer will be having? Any type of transformer you take, we have the two important elements. One is called as core. This rectangle one, which rectangle black line which represents the core of the transformer, and this circle type of one which the black lines which represents the winding, right? So the core, in the case of core type of transformer, the winding completely surrounds the transformer core. Again, I am repeating. In the case of core type of transformer, the winding which will surrounds the transformer core. So this is the transformer core, right? This is transformer core. Surrounds to that transformer core, we will have the winding. Or we can say that the winding which completely surrounds the core, or we can say that the core is surrounded by the winding. So this is what which we have in the case of core type of transformer. In the case of shell type of transformer, exactly the reverse case of construction will be there in the case of core type of transformer. Same in the case of shell type of transformer also we have that is a transformer core and as well as the winding. Now while compared with the core type of transformer, the only difference that we have here it is there the transformer core is surrounded by the winding, but in the case of shell type of transformer, the winding which is surrounded by the transformer core. So this is the winding, this complete winding which is surrounded by the transformer core, right? So based on this construction, we have two types, that is a core type of transformer and as well as the shell type of transformer. Okay. And the next what we have discussed, next important thing that we already studied is the EMF equation. So transformer mainly works on the principle of mutual induction, right? What is mutual induction? How the transformer which works based on the mutual induction, that I will explain you. Once we will go through the starting circuit diagram, then I will explain you the principle of operation, how the transformer which will works based on mutual induction. See, to the primary winding of the transformer, we will give the AC excitation. Here V1 is the input voltage I am giving to the transformer. Here the sinusoidal voltage I am giving or I am applying to the primary winding of the transformer. Okay. So whenever you give the sinusoidal input voltage as input for the primary winding of the transformer, what will happen? The current, primary current which will flows. Here I1 which represents the current, primary current flowing through the transformer. Whenever I am applying the sinusoidal voltage to the primary winding, then it causes the I1 current to flow through the primary winding of the transformer. Okay. So now whenever an alternating current is flowing through the primary winding, what will happen? When current is flowing through the winding, then automatically flux will be produced. So the type of flux produced here also going to be, it is sinusoidal in nature only. Whenever you give the sinusoidal input voltage, the respective current flowing through the transformer is also going to be sinusoidal. Also the flux produced is also going to be sinusoidal in only. So this is sinusoidal flux. Here inside this rectangle, a dotted line which have been represented. This dotted line which represents the sinusoidal flux phi. It is the sinusoidal flux which is represented with the letter phi. Okay, this is transformer core. This is primary winding. This is called as secondary winding. Here N1 which represents what? N1 is nothing but a number of turns. Here the winding, the primary winding is there now. This primary winding consisting of the turns, right? In terms of turns we will count it. So that number of turns which is called as N1. Here N1 which represents the number of turns that we have in the primary winding. Similarly, this side, on the secondary side also we will have the secondary winding. This secondary winding consisting of the number of turns which is called as N2. So this N2 which represents the number of turns present in the secondary winding. V1 which represents the primary voltage, I1 which represents the primary current, N1 which represents the number of turns in the primary. Okay. So whenever you give the alternating voltage V1 which causes alternating current to flow through the primary winding, this alternating current I1 which produces the sinusoidal flux phi in the transformer core. So this flux which crosses both primary winding and as well as the secondary winding. Just by looking into this diagram, we can come to know that the alternating sinusoidal flux which crosses both primary winding and as well as the secondary winding. Okay. So now whatever the flux which was produced, it is crossing the primary winding, and due to which what will happen? There will be an induced EMF in the primary winding of the transformer. So whenever this sinusoidal flux, alternating flux, which is crosses by the stationary conductors, that is N1 number of turns, then there will be an induced EMF in the conductor or an induced EMF in the primary winding, and that EMF induced in the primary winding which is represented with E1. Okay, this E1 which represents the amount of EMF induced in the primary winding. Okay, so whenever you are giving the sinusoidal input voltage which causes I1 current to flow, this causes the sinusoidal flux phi to be flow through the transformer, and this flux which crosses the stationary conductors present in the primary winding, which resulting in, according to the Faraday's laws of electromagnetic induction, there will be an induced EMF in the primary winding of the transformer. And this EMF, what we are calling it as E1. E1 is nothing but the amount of EMF induced in the primary winding of the transformer. Okay, so from this simple thing, what we come to know, whenever you apply the alternating voltage to the transformer, there will be an induced EMF in the primary winding. So this alternating flux is not only crossing the primary winding, also it is crossing to the secondary winding. So resulting in there will be an induced EMF in the secondary winding also. So this amount of EMF induced in the secondary winding, what we are calling it as E2. E2 is nothing but the amount of voltage which induces in the secondary winding. Okay. So whenever EMF produced here and this is secondary winding through load which is a closed one. So the secondary winding, whatever the voltage which induces, that drives the current to the load, and that current what we are calling it as secondary current, and it is represented with I2. So here I2 which represents the secondary current, E1 is the primary voltage, E2 is the secondary voltage, and V2 is nothing but the amount of voltage across the load. So this is about this is what the working principle of the transformer and how the transformer works based on the whenever a sinusoidal input voltage that you have been given. So the type of EMF induced in the transformer is called as statically induced EMF. Okay. So these concepts which we already studied, and just for retrieve that whatever the concepts that we have studied. This is how the transformer basically function. Now, if we go to the EMF equation of the transformer directly, final equation I am putting here. So this is the equation E1 which represents what? The amount of EMF produced in the primary winding, and similarly E2 is nothing but what? The amount of EMF induced in the secondary winding. So the what is the equation for amount of EMF induced in the primary winding? E1 is equal to, we have 4.44 phi maximum F into N1. Here E1 is nothing but amount of induced voltage in the primary winding, phi m, where phi which represents the flux. Okay, already shown in the schematic diagram, and F here which represents the supply frequency. Okay, and N1 already we know, N1 which represents the number of turns of the primary winding. So the amount of EMF induced in the primary winding we can calculate by this simple equation 4.44 phi maximum F into N1, and this equation what we are calling it as the EMF equation, and this equation which helpful in the calculation of EMF induced in the primary winding of the transformer. In the similar way, the amount of EMF induced in the secondary winding E2 can also be calculated, and this amount of EMF induced E2 is calculated by the simple equation 4.44 phi maximum F into N2. The only difference between this E1 and E2 in the equations is, here in the calculation of EMF of the primary winding, we will multiply this factor with N1, and when calculating the amount of EMF in the secondary winding, we are calculating with the term which is called as N2. Okay, so if you simply multiply with the number of turns in the primary winding of this term, simply we will get the amount of EMF induced voltage in the primary winding, and simply if you multiply with the number of turns in the secondary winding, then we will get the EMF induced in the secondary winding. And simply from these equations, we also derived voltage transformation ratio, and this transformation ratio K, which is given by E2 by E1 is equal to N2 by N1. From this equation, if you simply divide the first equation with respect to the second equation, that is E2 by E1, if you do what we will get 4.44, 5 maximum F will be get cancels in the two equations. So N2 by N1 we will get. So that is what which I have written here. E2 by E1 is equal to N2 by N1, and this ratio what we are calling it as voltage transformation ratio, or simply we can call it as transformation ratio of the transformer. Okay. Just wait, I will stop the recording, and if any doubt if you have, then you can ask me. You can unmute from your side, and if you have any doubt, you can ask me. Till now, whatever the concept that we discussed, if you have any doubt, you can ask me. Afifa, unmute from your side. Ishrat, any doubt in the concept which we have discussed so far? Guys, unmute from your side. Hello. ಏನಾದರೂ ಡೌಟ್ ಇದೆನಮ್ಮ? ಸಹನಾ, hello. Hello. Okay, again we'll come to the class. So the next topic that we covered in the basic electrical engineering is losses in a transformer. So how about the construction? What is the transformer? Why we use the transformer, right? What is the working principle? Already we covered. So the next important topic that you already studied is losses in a transformer. Okay, any transformer, if you take we have various losses that are taking place in the transformer. So what the losses that will be taking place in generally, there is two important classification we have. One is core losses, or we are calling it as iron losses. One more is copper loss, or we are calling it as winding losses. As we know, the transformer having the two important parts, right? One is transformer core, and the another one is winding. So the losses which taking place in the transformer core is called as core loss. Simple. Whatever the losses that were taking place in the winding, which is called as copper loss. Okay, winding here it is made with iron material. In the olden days they were supposed to use the iron material, and that's why this core loss, which is also named it as iron loss. Okay, the winding which is made up with the material called as copper, and that's why the losses that were taking place in the winding, which is also called as copper loss. Okay, so let me explain you what is this core loss and as well as the copper loss in brief. So here the core loss means there is these consisting of again core losses, again two types of losses it is having. One is hysteresis loss and the another one is eddy current loss. Both these losses combinedly we are calling it as core loss or iron loss, or also another name for this is a constant loss. Okay, now first let me explain you about what is hysteresis loss. Hysteresis loss means this is the loss which is due to continuous magnetic reversal of the magnetic polarities in the transformer core, and the formula which we are using to calculate the hysteresis loss in the transformer, which is given by here it is there. WH is equal to KH into F into B maximum power 1.6 watts per meter cube. Here WH, which represents the amount of loss taking place, hysteresis loss taking place in the transformer, where KH is nothing but hysteresis coefficient or hysteresis constant, F is the supply frequency, and B maximum is nothing but the flux density in the transformer. Flux density is nothing but what? Flux per unit area. So that's why the flux density which is measured in Weber per meter square. Okay, flux density is nothing but flux per unit area. Unit of flux is the Weber and a unit of area is meter square. So flux density unit which will becomes Weber per meter square. So this is what the formula, empirical formula, which we are using to calculate the hysteresis loss taking place in the transformer. Next, coming to the eddy current losses. This is another type of core loss that was taking place in the transformer. So eddy current loss is nothing but it is a loss which is due to the eddy currents set up in the transformer core. So in the case of whenever the transformer core is there, there will be the formation of eddy currents in the transformer core, and these eddy currents which produces are which having some loss, and that loss what we are calling it as eddy current power loss. Okay, this eddy current power loss which is denoted with the letter which is called as WE. WE is represents, E here represents eddy current, W which represents power. Okay, so eddy current power loss anta meaning. So these eddy current losses which are due to the eddy current setup in the transformer core. When the flux is linking with the core changes, it is given by the eddy current loss. So the empirical formula to calculate this eddy current power loss, which is given by WE is equal to KE into F square B maximum square T square. Here KE is represents the constant, eddy current constant. Here F is as usual the supply frequency. The B maximum is nothing but the flux density. Here T represents the thickness of lamination. Okay, actually whatever the transformer core which we have, the transformer core, to reduce the eddy current power losses, a solid core instead of using, we will sectionalize the transformer core into the smaller laminations, and that process in that process we can reduce the amount of eddy current losses taking place in the transformer. Okay, so this complete process what we are calling it as sectionalizing the transformer core. Instead of using the solid core, we will sectionalize the transformer core into the thin laminations, and this T which represents the thickness of the individual lamination. How smaller this thickness of lamination it will be, that much greatly the eddy current losses which will be get reduces. Large thickness of the transformer core if you have, then eddy current losses will be very high. If thickness of lamination is reduces, then automatically eddy current power losses will be get reduces. So that's why instead of using the solid core in the transformer core, always we will use the thin laminations of transformer core. Okay. So this is about eddy current power loss taking place in the transformer. And next important loss taking place in the transformer is copper loss. Again, we have two copper losses, that is primary copper loss and as well as the secondary copper loss. Amount of copper loss taking place in the primary winding which is given by primary copper loss. The amount of copper loss taking place in the secondary winding is called as secondary copper loss. Okay. primary winding only flow the current I1. So due to the I1 current, there will be copper loss in the primary winding, and that loss which is given by I1 square R1. So this I1 square R1 which represents the amount of primary copper loss. Similarly, what is the current flowing in the secondary winding? I2. So due to this I2, there will be a copper loss in the secondary winding. So that loss, what we are calling it as secondary copper loss, and the amount of secondary copper loss we can calculate by I2 square R02 or I2 square R2. Okay, this is the amount of secondary loss. Why this copper loss which will be taking place in the copper winding of the transformer? So as we already know, whenever we give the excitation to the transformer, there will be a current flow in the transformer. So when the current is flowing in the windings of the transformer, the windings which made with the conductive material which consisting of some small amount of finite resistance. So when current is flowing through the resistance, then definitely due to the resistance there will be a amount of power loss, and that loss what we are calling it as copper loss. So what due to the primary current, whatever the amount of copper loss which taking place, it is called as primary copper loss. Due to the secondary current, whatever the loss which taking place in the secondary winding is called as secondary copper loss. Okay, so this is about the various losses that were taking place in the transformer. Next, the efficiency of the transformer. What is meant by the efficiency? The efficiency is nothing but it is a parameter which calculates the performance of the transformer. Okay, so the efficiency of the transformer, which is defined as the ratio of output power to the input power. Output power we can calculate by simply whatever the output power, nothing but we will calculate across the secondary winding. Input power is nothing but we will calculate across the primary winding. So output power, simply the ratio of output power to the input power, if you calculate, then you will get the efficiency, and efficiency is denoted with this symbol eta. And if you want to calculate the percentage efficiency, simply just multiply this term with 100, then percentage efficiency we will get. Okay, so this is about the efficiency, and this is what the formula which we have to calculate the percentage efficiency at any load conditions. Okay, and nextly maximum efficiency condition, or we can say that condition for maximum efficiency. We actually derivation to, we have derived the complete condition how we will get the maximum efficiency. So I will just not going through the complete derivation, directly the result I will kept in front of you. What is the condition we have to get the maximum efficiency of the transformer? The iron loss taking place in the transformer must be equal to the copper losses taking place in the transformer. Or simply we can say that at a particular load condition, if the amount of iron loss taking place in the transformer exactly equals to the copper loss taking place in the transformer, then at that instant or at that load condition, we will have the maximum efficiency of the transformer. Okay, so already we derived that condition in the previous classes only, that is in the basic electrical engineering I derived that. So we already know the condition for maximum efficiency also. What is that condition we have? The condition for maximum efficiency is the amount of core losses taking place must be equal to the amount of copper losses, or we can say that the amount of constant loss. Iron losses are called as constant losses, and the copper losses are called as variable loss. So the amount of constant losses when equals to the amount of variable loss, at that instant we will get the maximum efficiency of the transformer. This is the curve which represents the percentage of efficiency with respect to output. So the efficiency curve we will get like this with respect to output load condition. If you draw the efficiency curve, then we will get like this. Okay, this is the efficiency curve. And next, voltage regulation of the transformer. What is voltage regulation? Voltage regulation is nothing but it is the ratio of changing in secondary terminal voltage from no load to full load. So during the no load, whatever the secondary voltage that we have, that is called as no load secondary voltage. During the full load, whatever the load or secondary voltage we have, that is full load voltage, full load secondary voltage. So simply the difference between no load and full load voltage divided by no load voltage, this ratio which is given by voltage regulation. And simply if you always we will represent the voltage regulation in terms of percentage. So percentage voltage regulation, which is if it is given by multiplying with 100. Okay. Always a better transformer should have the better efficiency, that is the highest the value of efficiency if you have, then it is called as the better transformer, and always we will have the less value of voltage regulation. Okay. A transformer which is having the highest efficiency means nearer to 100 if you have, then it is called as a better transformer. A transformer, two transformers while you are comparing with respect to the efficiency, which one is said to be the best transformer? Which transformer is having the highest value of efficiency? That is a good transformer. Andre, suppose one transformer ನನಗೆ 90% efficiency ಇದೆ, ಇನ್ನೊಂದು transformer 80% efficiency ಇದೆ. Which one you say that a good transformer or the best transformer among these two? We can say the better efficiency which one is having, that transformer is always good in performance. Okay, and that is with respect to the efficiency. With respect to the regulation, which one is said to be the best transformer or better transformer? The transformer which one is having the lesser voltage regulation is always best one. Okay, so andre ಎರಡು ಟ್ರಾನ್ಸ್ಫಾರ್ಮರ್ ಇದೆ, ನನಗೆ ಒಂದು ಟ್ರಾನ್ಸ್ಫಾರ್ಮರ್ 5% voltage regulation ಇದೆ, ನನಗೆ ಇನ್ನೊಂದು 2% ಇದೆ. So which one is better transformer in among these two? The transformer whichever having 2% of voltage regulation is always better transformer. Okay, so always a best transformer should have the highest value of efficiency and the less value of voltage regulation. Okay, so this is about the prerequisites about the concepts about the transformer. And in this one, if you have any doubt, you can ask me. In the next class, I will start the module 1. Okay. Participants, you can unmute from your side, and if you have any doubt, you can ask me. Dear students, I have stopped my class. With this, I am stopping my class. And so far, whatever the concepts that we discussed in this, if you have any doubt, you can ask me. There is no doubt. Hello. Unmute ಮಾಡ್ಕೊಳ್ರಮ್ಮ, ಎಲ್ಲರೂ unmute ಮಾಡ್ಕೊಳ್ರಿ.